Lesson 3. Creating an Application Architecture. This lesson will cover architecture testing, LabVIEW style guidelines, user events, the queued message handler template, application data types, and notifiers. System-level tests are important for evaluating all aspects of your application. Click on each of the types of tests below to learn more. Configuration tests are used to validate the system in a variety of different software configurations, such as different hardware configurations, different screen resolutions, multiple operating systems, or other system-level differences. Functionality tests are used to validate that the software meets the functional requirements stated in the requirements document. Performance tests are used to validate that the program meets minimum performance requirements. These tests can include benchmarking for execution time, memory usage, file size, and other performance-related metrics. Reliability tests are used to verify that the application functions in a non-development environment. These include tests such as alpha testing and beta testing. Alpha testing is the first viable release of the program and is generally used to validate basic system functionality. Beta testing begins when most of the system is operational and implemented and ready for user feedback. During beta testing, the customers in the field test the product. Stress or load tests push a program beyond its designed limits and are generally used to determine where unexpected failures may occur. Usability testing evaluates the user-friendliness of your program. This involves allowing end users access to the application so that they can provide useful feedback on features in the application. The LabVIEW Style Guidelines is a set of recommendations that helps keep code scalable, readable, and maintainable. Spend a few minutes to explore some of the different style guidelines. In this example of an event-driven producer-consumer architecture, what is the best way of stopping both loops? All of these solutions share the same problem of requiring a timeout on the event structure or waiting for an event to occur before stopping the top loop. The best possible solution would be to trigger an event that stops the top loop programmatically. The way we can do this is with user events. There are several steps to setting up user events. The first is to create the user event and then register it to an event structure. From there, you can generate user events programmatically at any point in your code. Unregistering and destroying the user event frees up the resource. When creating a user event, you have to define the user event's data type. If using a constant, make sure that you set the label on the block diagram. This is what defines the name of the event in the event structure, similar to a control on the front panel. The next step is to register the events with the event structure by using the Register for Events node. Finally, right-click on the event structure and select the Show Dynamic Events terminals. Wire the output of the Register for Events node to this to complete registering the events to that event structure. Once your events have been created and registered to the event structure, they will show up in the Add Events case underneath Dynamic Events. Remember that dynamic events are named after the label on the input on the Create User Events node. From this point on, you can treat the event structure as you normally would as if the events were being generated by normal front panel activity. To generate a user event, use the Generate User Event node. You will have to send data along with this event. Note that you need to wire the user event wire into this and not the registered event refnum. Unregistering for events stops the event structure from responding to dynamic events. Destroying user events frees up the event resource. Events are also released when the top-level VI stops running. Spend a few minutes exploring the user events demonstration VI. The user event data type in this example is an error cluster. If the sub-VI in the consumer loop generates an error, the Generate User Event function will send the user event with the associated error data to the event structure registered to handle the event in the producer loop. The event structure in the producer loop then executes the code in the error user event case. The producer-consumer events design pattern efficiently passes messages from the producer loop to the consumer loop. You can use the events to send messages from the consumer loop back to the producer loop. The queued message handler template draws from both the state machine and the producer-consumer architectures to create a robust design template that is well suited for medium to large-scale LabVIEW applications. It combines the functionality of the state machine with the responsiveness of the event-driven producer-consumer architecture. The queued message handler is based off of the idea of sending messages. A message consists of an instruction and any data needed to execute that instruction. The queued message handler template is broken up into two loops. The top loop handles user interface interaction, while the bottom loop handles all of the messages. Both the event handling loop and the message handling loop are capable of sending messages. In this way, the message handling loop can act like a state machine and change its internal state. The queued message handler uses queues to pass data between independent loops. This allows each loop to run at its own independent rate. Multiple different loops can generate messages for the message handling loop. The message handling loop can also generate messages for itself. The queued message handler template provides several additional features, such as a messaging library for queue management, a user event library to create the stop event, and basic error handling. This is the queued message handler project template. When you create a new project from this template, it will create a main VI and two supporting libraries, one for messaging and the other for user events. The main VI contains two generic buttons, a display string and an exit button. Running it, we can see that these buttons have some basic functionality attached to them. When the Do Something button is clicked, the message changes. When the Do Something Else button is clicked, the message changes again. Closing the VI or pushing the exit button will stop it. Let's have a look at the code behind this. This is the basis of a queued message handler. Notice there are several similarities between this and the producer-consumer architecture. One of the main differences between the queued message handler and the producer-consumer architecture is that the consumer loop in the queued message handler has access to its own queue and can enqueue other elements onto it. In this way, it acts similar to a state machine, able to transition between states without external input. On the left-hand side, outside of both loops, we can see some initialization code. In this code, we obtain queues, create a user event, and register the user event. Looking at the event structure in the top loop, we can see that each case enqueues a message onto the queue. Looking at the lower loop, the message handling loop, we can see that the first thing that occurs is a dequeue. When a message is dequeued, it is broken up into its messaging component and its message data component. When a message is dequeued, the case structure then executes based on the message received. Looking at the initialize case, there are several interesting things to point out here. The first is fairly standard in that we are initializing panel references, in case we need to use front panel objects in sub-VIs. The interesting part is here, where we are enqueuing a message to ourselves to update the display. This is one of the main differences between a queued message handler and a producer-consumer architecture. Allowing the message handling loop access to its own queue to enqueue messages to itself is a key feature of the queued message handler. Looking at this case, we can see that the update display message will run immediately after the initialize case has run. Another interesting feature of the queued message handler is the shutdown procedure. Since our message handling loop is the heart of our program, all shutdown requests need to be processed by it first. A shutdown request could come from a user pushing the stop button, attempting to close the application, or from other sources, such as an error. In the event of a user trying to close the program, we go to the confirm quit case. In the event that the user tries to close the application, we execute the confirm quit case. In the template, this executes the exit case immediately, but it would be a good place to put a dialog box for confirmation. An important thing to note here is that the panel close and exit buttons do not exit the event handling loop. When we execute the confirm quit case, we then go to the exit case. In the exit case, we send the stop event to stop the event handling loop. We release the queue and exit the message handling loop. It's important to note that the only way the event handling loop can be shut down is through this stop event.
For this development sprint, your team has identified 2 user stories that apply to the overall system architecture. Your team then determines the development tasks that are needed to implement these user stories. Your team then decides to use a queued message handler to implement the top-level architecture based on the need for parallelism and the possibility of messages being generated from multiple processes. In addition to the default event handling loop and message handling loop, you determine that the application will need a third loop to handle communication with the boiler. When we run main.vi, first we encounter the dialog letting us know that we reached the initialize case of the boiler controller loop. So I'll click OK, and now when I click on the stop button, we see that all of the parallel loops shut down successfully. For this exercise, as well as other exercises throughout this course, the development sprint will end with testing your ability to deploy the application. Let's take a look at the solution to exercise 3-1. In boilercontroller.lvproj, let's open main.vi. This VI is the top-level VI for our application. If we open the block diagram and then scroll to the far left, we can then open createAllMessageQueues.vi. One of the first things that we should notice here is that message queues out contains 2 references. The first is a reference to the message handling loop queue. The next is a reference to the boiler controller queue. If we look at the block diagram for this VI, we can see that in addition to creating these queues and creating that cluster, we're also sending an initialize message for both of those queues. Now let's take a look at how each of those processes handles the initialize message. In the message handling loop, there was already an initialize case created by the queued message handler template. We're not going to spend a lot of time talking about the functionality here because, frankly, we're going to go and replace it all as we implement the user stories around initialization. Instead, let's go down and take a look at the boiler controller VI that we created. If we open the block diagram for this VI, we can then navigate to the initialize case, and we see that the functionality here is very simple. We're just using a one-button dialog to display a very simple message to the user saying that, hey, we received the message and we got to the initialize case in the boiler controller loop. In addition to this case, we also implemented a case for the exit message, wherein we're just going to release the queue, and then we're going to stop the VI by setting a true constant over to the stop condition for the loop. But how do we get that message, that exit message within this loop? Let's take a look back at our message handling loop, and now we'll go over to the exit case. When the exit message is received by this loop, three things happen. The first thing that happens is that we send that exit message down to our boiler controller. The second thing that happens is that we send a stop event to the event handling loop for this application. The third thing that happens is that we release the queue for this message handling loop. So let's take a look at what happens with that stop user event. When we send that user event up to our event handling loop, the first thing that happens is that we display a message to the user just indicating that the VI has been stopped. The next thing we see is that we have a true constant that wires out to the conditional terminal for this loop. So effectively, now when an exit message has occurred, we have stopped all three of our loops. So when that happens, you can see that we first destroy the user event that we used previously, and then depending on how this application is running, in this case, if it's executing as part of an executable, then that means that we're going to call the quit LabVIEW function when this VI exits. Components of the Queued Message Handler project template are largely intended to be starting points to leverage and build from. Some components, like the stop user event, can be easily reused in multiple applications without having to make any modifications whatsoever. This application contains 3 loops, 2 in the top-level diagram and 1 contained in a sub-VI. It's best to keep the event handling loop and the message handling loop in the top-level VI because those loops are reusable architectural components that you can apply for a variety of applications. They also control the flow of the project. The boiler controller loop is in a sub-VI because it's application-specific. You can encapsulate it in a sub-VI to make your application more modular. You can also easily replace this sub-VI with another controller sub-VI for another application if you need to. Placing that code within a sub-VI makes the top-level VI much easier to manage and easier to read.
The Continuous Measurement and Logging project template is an example of one way to use a queued message handler for a medium-sized application. In this example, we have several buttons, a dialog box, and a graph. When we run this code, there is no immediate obvious activity. However, we can click on Start to begin data acquisition, and Stop to stop it. Notice that as I push the buttons, the string indicator changes from ready to acquiring. I can also launch a dialog box for the settings that allows me to change the signal type and the log path. Starting it again with the sine wave setting, it generates a sine wave. Pushing the exit button or closing the window stops the program. Looking at the code from this, we can see that it is very similar to the queued message handler template that we just looked at. There's still the event handling loop and the message handling loop. However, we have 3 additional loops: an acquisition manager, a logging manager, and a data display loop. The acquisition and logging loops share several queues for data communication as well as messaging. The state that the front panel is in is stored as an enum in the message handling loop. This allows us to set different states for enabling and disabling a set of controls. The data display loop uses a notifier to get the latest data from the acquisition loop and display it on the graph. The logging loop receives a queue from the acquisition loop and logs all of the data to disk when configured to do so. If we have a clearly defined set of messages that the acquisition and logging loops can receive and generate, we could conceivably drop these into another program with minimal problems. This is the idea behind the queued message handler template and how it promotes code reuse. Variants are a LabVIEW data type that act as a generic container for all other LabVIEW data types. The toVariants node converts any LabVIEW data type into a variant. The variant2data node converts a variant back into a LabVIEW data type. The variant2data requires the type to be defined at edit time and will result in an error at runtime if there is a type mismatch. The data type defined for your queue will define how your application passes data between parallel loops. It is common practice to have a type-defined message cluster that contains two elements, one for the message and one for any pertinent data. Since your messages may be sending varied or unknown data types, it's a good idea to select an adaptable data type such as a string or variant for the data element of the message cluster. Strings or enums make a good candidate for the messaging component of the message cluster. The benefits to strings are that they can be created programmatically and make specifying messages easy. They are also easier to localize. The benefits of enums include that you can limit the number of available messages and can't accidentally send the wrong message. Strings and variants are a good choice for the data component of the messaging cluster. Both can be adapted to fit any LabVIEW data type through the flatten and unflatten from string or toVariant and variant to data nodes. Recall that queues function well in a one-to-one or many-to-one communication model. They buffer data and dequeue a single element at a time. Notifiers, on the other hand, are more suited to a one-to-many communication model and can trigger multiple sections of code to execute simultaneously. Notifiers do not buffer data and only the latest notification is available. Both queues and notifiers will suspend execution while waiting on an element to be available. Obtain notifier defines the data type for the notifier and creates the reference. Wait on notification suspends execution until a notification is received, or a timeout occurs if configured. Multiple wait on notification nodes can wait for the same notification. Get notifier status returns the value of the last notification sent. Release notifier destroys the reference and frees up the resource. There are three common use cases for a notifier. The first is for synchronizing multiple processes to occur at the same time. The second is handshaking, where a notifier can be used to inform a process that an action has been completed. And the third is to act as a lossy queue to update a value. One send notification will trigger all wait on notification nodes that are currently suspending execution. This is a major difference between queues and notifiers. If a queue has 10 dequeue element functions wired to it and an element is enqueued, only one of the dequeue element functions will execute. If there are 10 wait on notification functions wired to the same notifier and a notification is sent, all 10 functions execute at the same time. In this course, we will use notifiers as a handshaking mechanism between the boiler and the boiler controller. The boiler controller will send a message to the boiler and then immediately wait on a notification to receive confirmation that the boiler received the message and executed the appropriate command.
In the sprint planning meeting for this iteration, the product owner chose to implement two user stories that apply to the interaction of the boiler controller application with the boiler. After discussing each user story with the team, you identify development tasks that you must complete to implement these user stories. Earlier, you created a project library that contains code that simulates the behavior of the boiler that the application is going to control. From this library, you add the boiler as a fourth parallel process for the application. When we run main.vi, first we encounter the dialog letting us know that we reached the initialized case of the boiler controller loop. So I'll click OK, and now when I click on the Stop button, we see that all of the parallel loops shut down successfully. In this exercise, you will add the boiler process to the top-level VI and use notifiers to implement handshaking between the boiler controller and the boiler. Now let's take a look at the solution to exercise 3-2. Within this project, let's first look at support VIs, notifiers. Here we've got notifiers.ctl and the VIs that we're going to use to create, close, and send notifications from the controller loop to the boiler loop. Also within the project, we've added boiler.lvlib. Recall that we created boiler.lvlib in an earlier exercise. When we add the library to this project, in addition to including the VIs that we added to the library, we also maintain the access scope that we set. Now let's look at main.vi. When we look at the block diagram, I want to first point out that we've added boiler.vi. This VI basically handles the functionality of the boiler. We're not going to mess with that yet because that was provided to us by another developer. Now let's take a look at boiler system open. This VI contains some of the functionality that we used earlier for setup, but it also includes a new VI that we've created to create notifiers. When we look at this block diagram, we see that we're still creating our user event, we're still creating our message queues, which in this case now includes a queue for the boiler loop, and we've got create notifiers.vi. When we look at create notifiers, here we see that we're creating 4 different notifiers. Now within this exercise, we're really only going to work with the controller exit and boiler exit notifiers. The handshake and flame level notifiers we'll work with later on in the course as we implement additional boiler functionality. Now let's look at how we handle a shutdown event. That event is going to be generated by the user clicking on the stop button. When the user clicks on the stop button, in the event handling loop we send a message to initiate stop, and that message gets sent to our message handling loop. Within the message handling loop, when we go to the initiate stop case, we see that first we send an exit message to the boiler controller, and then within this same loop we wait on notification from the boiler controller. Next, let's take a look at the boiler controller and see what it does with the exit message. When we open the block diagram and we look at the exit, we see that first we're going to send a message to the boiler loop for it to exit. And then once it sends that message, we're going to wait within this sub-VI for the boiler to send a notification back to the boiler controller that it has successfully shut down. Once that notification is received, then we release the queue and send a notification back to the message handling loops indicating that we have successfully shut down the boiler and the boiler controller. So now let's look back at the message handling loop and see what happens there. So, as I mentioned earlier, after we send the exit message, we then wait for the boiler to exit. When we look at the wait on boiler exit case, here we're waiting for that notification to be sent by the boiler controller. Once the notification is set, then we're going to go to the exit case for this loop. Before that notification is sent, we're going to continue just waiting, going back to this wait case. After this loop shuts down, we see that when we go to the exit case, same as before, we're going to send the stop user event up to the event handling loop, and then we release the queue. When I look back up here, recall that within the user event case, we're going to stop the execution of this loop. And once all 4 of our loops have finished shutting down, then we go to our shutdown code, where now we've included a VI that closes the notifiers that we created earlier. One of the risks of using notifiers is the possibility of a process missing a notification because it's busy handling a previous notification. You might find yourself wondering, how does the application make sure that no notification is missed? Since controller.boiler.vi sends a message to boiler.vi and immediately starts waiting, there is no chance that the notification will be missed. Boiler.vi contains the code to send notifications when it completes each task that it receives from the boiler controller. Boiler.vi is the only source of creating that handshake notifier.
You have completed this lesson. Here's a summary of what we covered.